All high pressure aeroponic systems need some form of tubing. Are you using the right tubing? Your aeroponic system must use tubing. If you use the wrong tubing, your system will fail. Not if, it's when. So let's go through the tubing that we should use for high pressure aeroponic systems. First, let's talk about the characteristic and the composition of tubing. Now, tubing comes in different color sizes, different thicknesses, different diameter, and different material. Now, we want to stay away from using any metal tubing like stainless steel. And so therefore that narrows it down to some type of polymer. Preferably use a polypropylene tubing. And we want the tubing to be opaque. We don't want light to enter the tubing. If we have light entering our tubing, then we have a high chance and a high probability that algae will form. We have to remember that we have grow lights, LED lights, or sunlight exposing our plants. That's a lot of high intensity light. So if your tubing is not opaque, that light will enter the nutrient and cause bacteria, algae, and other things to grow that will contaminate your system. If any of your tubing is white, it is not opaque. I recommend that you replace that tubing as soon as possible to an opaque tubing because your system will fail eventually. And so remember again, I want to emphasize this. With the aeroponic system, we are using lights that are very powerful. Either we're using grow lights, or we have sunlight, or we're using LEDs, and we're running it longer. If any of your tubing is exposed to this light and it's not opaque, and definitely if your tubing is white, you will pay dearly. Your system will fail. It is not if, it's just when. And one of the problems will be clogged nozzles. I never suffer a clogged nozzle because I use black opaque tubing. So I recommend that you stay with black. Don't use any colors, just stay with black tubing. So most of this tubing you will find at water purifier companies. Those who manufacture reverse osmosis and filtering for the house. Or they will use the tubing for attaching a ice maker to your refrigerator. So if you choose this type of tubing, it is compliant with your state law to be food compliant. So make sure that it is black and opaque, and that the tubing was devised for drinking water, so that you know that it be safe to use in your high pressure aeroponic system. Okay, so now let's talk about the capabilities of the tubing. So there's two things we need to keep in mind is that the working pressure that the tubing is rated for and the temperature. The temperature and the working pressure work hand in hand. Very similar on how the fittings work hand in hand. When you have higher temperatures, the working pressure capacity, the maximum pressure that you can expose it to will drop. Tubing is the same thing. So when a tubing is rated, normally they rate it at around 73 to 75 degrees. So when they tell you the tubing is rated for 200 psi or the tubing is rated for 250 psi, that test was done when the fluid running through the tube was at 73 degrees or around 75 degrees, which is about 20 Celsius. So keep that in mind. So if we have a tubing that's rated for 200 or 250 psi at around 73 degrees Fahrenheit, if we're going to be running up to 100, okay, you have to remember that that number will almost be cut in half. So that means that if the tubing is rated at 200, then don't expect to run it more than 100 psi if you're going to be running the temperature up to 100 degrees. or if it's rated at 250, don't run it above 125 psi. So most of us, if we are using the recommended pump of 80 to 100 psi, we are okay using most standard low pressure tubing, which we will be using. So keep that in mind. So if the tubing pressure is rated at 200 to 250 psi, that test was done when the liquid was at 73 degrees Fahrenheit. So if you're running warmer than that, keep that in mind, that you have to drop the pressure, maximum pressure rating for that. Okay, another thing to keep in mind is the tubing dimensions. When it comes to your dimensions, normally you have two things to deal with. One is the diameter, okay, the diameter of the tubing, and another one is the wall thickness of the tubing. Okay, so the diameter is normally the outside diameter of the tubing. Sometimes they would give you the inside diameter of the tubing, and let's use the 1/4 inch tubing because that one I know pretty well. Okay, so in the 1/4 inch tubing, okay, this here is the outside diameter, which is a 1/4 inch, which is 0.25 inches. Okay, this tubing has a wall thickness of 1/16 of an inch. So therefore, we gotta double the wall thickness to come up with the inside diameter. Okay, so since this is a 1/4 inch tubing, we take 1/16 times 2, which equals 1/8 of an inch. That means that we are left with 1/8 of an inch of the inside diameter. So this tubing, the inside is only 1/8 of an inch for a 1/4 inch tubing. Now the question is that when you choose a tubing, you want to be careful to not to choose a tubing where the wall thickness is so thick that the inside diameter is less than 1/8 of an inch. We don't want to go below 1/8 of an inch for a standard high pressure aeroponics system. So now that comes to the question of size. Which size should you use for a high pressure aeroponics system? The two most common sizes are a 1/4 inch and a 3/8 of an inch tubing. So I noticed that some of you are using 3/8 inch, but if you don't know why you're using a particular size of tubing, then most likely you're using the wrong tubing. Let's use some physics here, and let's talk about the Bernoulli equation, which is basically an equation of conservation of energy. So think of a scale, okay? So the energy on one side of the scale needs to match the energy on the other side of the scale. So that means that the equation has to be balanced. So let me show you the equation. This is the equation. So we see that on the left side, we basically have pressure, we have kinetic energy, and we have potential energy equals the pressure, kinetic, and potential energy on the other side. So that means that if we have a tube and we have liquid running through that tube, the energy being used to apply the liquid to the tube should equal the energy coming out of the tube. That's basically what the equation means. So the same energy being applied, the force, the pressure, okay, that's entering the tube should equal the same pressure and energy at the outlet of the tube. So it makes common sense that if you have water flowing through a tube with the same diameter, none of the characteristics changes, and you got water entering the tube, most likely the energy exiting the tube will equal the outside, meaning that all the parameters, the potential will be the same, and the kinetic energy will be the same, and the pressure on both ends would be the same. So if you got 100 psi here, you see 100 psi here. Now the equation takes into consideration when things change. When the tube is no longer at the same height, okay, where we have differences, and once we change the height of one end of the tube, the equation changes. What happens is that the pressure that's entering won't be the same on the outlet of the tube because of the height difference. Okay, so the Bernoulli equation helps us to figure out what happens when we're running a tube through an aeroponics system and we're running up and down through our chambers. What changes are we making in the flow of the nutrient running through the system? So let's talk about that. Okay, so one thing to keep in mind is that kinetic energy is the energy that's in motion. Potential energy is basically the energy at a rest. And when energy is at a rest, the most influence on that when it comes to not only the height above the ground, but gravity. So gravity of the earth, okay, which a lot of times is equal to G. So we got to keep that in mind in choosing which tubing that we should use, okay? Because based upon that analogy about gravity on the effects of the pressure in the system, because when we start to raise the tubing and say that our pump is pumping here, so say that our pump is pumping here and the outlet's over here. So we can see that the pump is at a lower elevation and the outlet of the tube is at a higher elevation. That means that the pressure are no longer the same. The pressure here is not the same as the pressure here. Because of gravity and because of potential energy is working against us, the pressure here has to drop. So if we're pumping 10 psi here, we're probably only getting 9 psi here because of the elevation. Now that's a very dramatic change. For this height, which is about maybe 16 inches, you won't see that much of a drop. It'd probably be very negligible that you can see any type of drop. But in our system, after you start running 2, 3, 4 feet of this difference, then the effects of gravity on the potential energy will start to rob the pressure reaching our nozzles. So the point is that if our pump is pumping 100 psi, our nozzles might be only getting 90 psi because it's so far above the pump. So the pump has to force more fluid through the tube to be able to get it to move. There's a back force. And let me illustrate this with 2 cups of water. Okay, so imagine that this cup here is the smaller tube. And imagine this cup or this glass of water is the larger tube. So you can see the difference. Okay, so imagine this is a section of the tube. Okay, and so let's talk about the smaller glass first. So let's say the pump, okay, is at the bottom of this column of water. Okay, and so the pump has to force this water up the tube. Okay, it has to force it up the tube and then move over to your nozzles to spray this water. Okay, so the pump has to actually fight, or it has to have enough energy to move this glass of water up inside the tube. Now this water has a certain amount of volume and mass, and so that means that the pump has to apply enough pressure to overcome the gravitational pull of this mass trying to fall to the ground. So you can see the amount of effort it will take to lift this volume of water. So imagine this is our 1/4 inch tubing. Okay, this is a 1/4 inch tubing, and this is the work that the pump have to use. Now let's change this glass to a larger glass of water. So imagine that this here is the 3/8 inch tubing. Now we have the same pump, we have the same nutrient. The only thing we change is that now we have larger tubing. That's the only thing we change here, okay? We still have the missing nozzles at the end. Now the pump has to have enough pressure to push this column of water up the tube and then over into our nozzles, okay, because now we have a larger tube. This glass, okay, is many times heavier than the other glass, meaning that the water column in a 3/8 inch of tubing is going to be much heavier than a column of water in a 1/4 inch tubing. So the pump has to work even harder to pump this glass of water, okay, over into a missing nozzle because it's heavier. So the pump has to work harder. Not only does the pump have to work harder, the pressure drop, okay, received at our nozzle is going to be even more. Let's say on the 1/4 inch tubing we had a 10 psi drop. That means that if you're pumping 100 psi, the nozzles are only getting 90. And this here, let's say that we're getting a 20 psi drop. That means that now our nozzles are only getting 80. Even though our pump is pumping 10 psi, because of the effort it needs to overcome the gravitational pull of this column of water, okay, it needs to force up the tube, it's going to lose about 20 psi before it gets to your nozzle. And that's what the Bernoulli equation helps us to figure out, that when the height difference of the inlet and outlet of a piece of tubing is great enough, we will lose pressure. So normally on a system, we won't lose a whole lot of pressure, but the pump will have to work harder to move that column of water. Now you might ask, well, I want to use a larger tubing because I want to make sure that I can move enough fluid, or I want to make sure that I can move my nutrient through the whole system. Otherwise it's going to be starving because I'm trying to push it through a small little piece of tube. The one thing you have to remember is that our nozzles are rated at gallons per an hour. So let's say that you're running a nozzle at 1 gallon per an hour. So that's 1 gallon per an hour. Okay, so based on that, how many gallons of water are we trying to push through our tubing? Remember, we're only misting for a few seconds, not that long. Okay, we're not really pumping a whole lot of water through our system. Let's say we're trying to run 10. Okay, so that means that we're saying that in 1 hour we'll be trying to pump 10 gallons of water. Okay, now that's in 1 hour. What if we take that 1 hour and break it down into a matter of seconds? How much water are we trying to pump through our tubing? So if we take roughly that we're doing 1 gallon per an hour per a nozzle, times it by 10, we're doing 10 gallons per an hour. So how many seconds are there in an hour? There are 3,600 seconds in an hour. So we take 3,600 seconds and then we divide our gallons per an hour by 3,600. That is for 1 second spray. So let's say that we're doing a 5-second spray. So we'll take that number and then we'll times it by 5 seconds. That means that when it comes to the amount of water that we're trying to push through in 5 seconds is just a little over 1/100th of a gallon. That means that we are not pushing much water through our tube when we're taking into consideration the second. So let's calculate the drop that we would get with a 1/4 inch tubing that's running 100 feet through our system. Now we won't get the exact number, but we'll get the ballpark of what a drop would be if we use a 1/4 inch tubing with misting nozzles that are rated at 1 gallon per an hour flow rate. So first, the chart that I will be using is using gallons per a minute. So the chart I'm using is using gallons per a minute. So let's convert the 1 gallon per an hour to gallons per a minute. So to do that, we take 1 divided by 60, because there's 60 minutes in an hour. That gives us 1/60th of a gallon would be per minute. Or another way we can state it, that it would be 0.0167 gallons per minute would be the flow rate. So that's 0.0167 gallons per a minute. Now, let's say that we're running 10 nozzles off of the same 1/4 inch tubing. So that means that our flow rate would be 10 times what it would be for a single nozzle. So if a single nozzle is 0.0167, that means for 10 nozzles the flow rate would be 0.167 gallons per minute. So let's round that to 0.2 gallons per minute. So that means that in our tubing with 10 nozzles that require 1 gallon per minute flow rate, that the combination of all 10 would be roughly about 0.2 gallons per a minute. So we kind of round up a little bit higher. So now let's look on our chart. Now if we look on our chart, we can see where it says at the very bottom of the chart is the pressure loss. Along the left side of the chart is the flow rate in gallons per minute. Now we have, this chart shows the different tubing of the inside diameter. So there's not really one here that's for our inside diameter, which is actually 1/8 of an inch, but the closest we have is 1/4 of an inch. Okay, so let's just use that one just for argument's sake. We just say that it's the same as the 1/8 inch inside diameter for our tubing. So we look at the 1/4 inch. Now if we take the 0.2 gallons per a minute, which is basically the very first number off the base, okay, and we go over, it's saying that we will lose roughly about 4 psi per 100 feet. So 100 feet of tubing, okay, of 1/4 inch inside diameter tubing, okay, running at 0.2 gallons per minute, it will lose roughly about 4 psi, okay, in 100 feet of tubing. Now what's interesting here is that if you wanted to know what the drop would be for 200 feet, you just double that number. So you double 4 to 8. If you wanted to know what the psi drop would be half of this number, like 50 feet of tubing, then you divide that number in half, so that would be a drop of 2 psi. So what we can say is that if we have tubing for our aeroponics system, we're not going to be running 100 feet. I think the most that any of you would ever run, okay, top would be 20 feet. That would be the maximum length of tubing running through your system would be about 20 feet. Okay, so if you're running a 1/4 inch tubing about 20 feet away from your accumulator, we can say, for argument's sake, that it's probably the same pressure drop as it would be 100 foot of cable. It'd be about the same pressure drop as 100 foot of true 1/4 inch tubing. So we can say that the pressure drop would be roughly 4 psi for a 20 foot long of our tubing. So if we are generating around 100 psi, then it would be 96 at the nozzle. At 80 psi, it would be 76 at the nozzle. Now what we could do, which is most cases you can do, you can adjust the pressure to be a little bit higher, maybe go to 105 psi to 85 psi as your range, and by doing that, that pressure drop will be compensated by producing a little bit more pressure. But remember what we mentioned earlier? Okay, so we have the height here. We have the height here, okay, with our volume of water. Now remember, this is going to take more effort to get the water up the tube than it would be for the smaller tube. So this is the 1/4 inch and this is the 3/8 inch. So what I'm trying to say here is that the loss that we gain because of the tube being smaller, we are actually gaining some psi because the tube being smaller too, because there's less volume of water for the pump to move. So this water here can move quicker, faster in our system than this column water, which will kind of move a little bit slower. We want speed, okay, through our system more so than volume. So that means that the 1/4 inch tubing, even though we could get a 4 psi drop at the nozzles, we are benefiting from running a smaller tubing. Number one, our pump doesn't have to work as hard, and two is that the price and parts that come with the cost of the tubing will be lower. Now, one thing that I didn't mention earlier about the tubing is that when we have a 3/8 inch tubing compared to a 1/4 inch tubing, it's obvious that the diameter of the tubing is going to be wider than the 1/4 inch tubing. So that means that when this tubing is under pressure, okay, and it's inserted into our fittings, okay, the 3/8 inches is inserted into our fittings, it has a more likelihood to deflect than a 1/4 inch tubing. What I'm trying to say here is that a 3/8 of an inch tubing will fail sooner in your system than a 1/4 inch tubing will. So what this means is that when it comes to maintenance, a 3/8 inch tube fitting will most likely need maintenance sooner than a 1/4 inch fitting tubing will. So we gain there again. And that's why I recommend for all high pressure aeroponic systems, I don't care how large or how small it is, that you use a 1/4 inch tubing for your system. Now, you might be asking, well, I have a whole room of aeroponics and yeah, I could be running 100 feet of cable. What can we do then? Well, there is another solution for you that's even better, and you still can use a 1/4 inch tubing for that insulation. So remember, if you're looking for tubing, if you don't know why you're using a particular size of tubing, then most likely you're using the wrong tubing. You should be sticking with 1/4 inch tubing, knowing that it means less stress on your pump, less likelihood to leak, and also too, the cost would be cheaper. Okay, so I hope that was beneficial for you, helped save you some time and money in researching all this information, and I did it for you, and my goal is to have everyone building their own high pressure aeroponics system. Bye! So please subscribe right here now on Aeroponics DIY and let us take you where no gardener has gone before.